All right, so we've got 1 kilogram of water initially at its critical point. If the water is cooled at constant specific volume to a pressure of 30 bar, we want to find the quality at the final state. So that's part A. Part B is we're going to say that, okay, we still start out at the same initial state, but we undergo a constant temperature expansion process to a pressure of 30 bar. And just FYI, if a process is constant temperature, it's called an isothermal process. So isothermal process. Yeah, constant temperature. And then, of course, we want to find show each process on a TV diagram. So, all right, so let's keep on going. So what's the critical temperature and pressure? Well, if you don't know that information, you can look it up in a couple of places. Table A1 has it. I've went ahead and put that temperature in terms of degrees Celsius, so they report it as 647.3 Kelvin. And that critical temperature and pressure, it's just the dot on the top of the dome, okay? So the critical temperature and pressure, they are specific for whatever substance that you've got. I can also find that critical temperature in table A2, so it is the very last line on those saturated tables. Now, what you'll notice is there's a little bit of a discrepancy between the critical temperature on the last line in A2 and within A1. So it's not that much different. You're talking about 374.14 versus 374.15. I believe this is probably just due to a little bit of a round off discrepancy. So I suspect that 647.3 was rounded off, or, there's a round off error somewhere. However, it's not anything really to worry about because I looked up the critical temperature for water on NIST's website, so NIST, National Institute of Standards and Technology, and they list the critical temperature as being somewhere between 647 plus or minus 2. So not a big deal, but what we're going to go with for the purposes of this particular problem is I'm going to go with a critical temperature of 374.14 degrees Celsius, but just because I'm going to be pulling some data off of table A2 and I just want to keep it nice and clean, keep the same value. So also, you could get the same information from table A3 that will also list the critical temperature and pressure, and it's just the last line on table A3, saturated tables for water organized by pressure. All right, so for part A, our final state is 30 bar and our specific volume is the same as at state 1. So I got to figure out, what is my specific volume at state 1? Well, it's going to be the specific volume at the critical pressure and critical temperature. So, all right, well, there you go. I know my critical temperature and pressure. What tables do I look in? Is that saturated? Is that compressed? Is it superheated? I don't know. Well, I just saw that that data is actually in my saturated table. So I'm going to go to A2, back to where I was, and I can see that at that critical temperature and pressure, my specific volume V sub F is 3.155, V sub G is 0.003155, and it's no coincidence that those numbers are exactly the same, not 3.155. V sub F is actually 0.003155 because that number has already been multiplied by 1,000. And it's really no coincidence that those numbers are the same, because for the critical point, the V sub F and the V sub G values are exactly the same. So there we go. There's my specific volume. And now I got to figure out, what do I need to figure out? I need to figure out the quality. Okay. All right. So I know that my pressure is 30 bar. So I kind of getting it out of your head, we were talking about state 1. Now we're going to use the information that we know about state 1. We're going to relate that back to state 2. So I'm solving for state 2 now, where state 2, my pressure is 30 bar and my specific volume is 0.003155 meters cubed per kilogram, because it's the same as at state 1. So at 30 bar, I go to my saturated tables to see what phase I'm in. Is it two-phase? Is it superheated? Is it compressed? And if that specific volume is between V sub F and V sub G, then I know it's saturated. I know it's two-phase. So my specific volume at state 2 is 0.003155 meters cubed per kilogram, and it is between the V sub F and the V sub G value. So, okay, so I know I'm two-phase, and I know what my temperature is because I just said I'm two-phase. The only temperature that it could be at is the saturation temperature at 30 bar, so 233.9 degrees Celsius, which means on my TV diagram, it's going straight down along a line of constant specific volume. and I'm kind of done with my TV diagram, and I've got everything that I need on there. I've got the temperatures listed, T1, T2, those are defined. I've got the specific volume, V1, V2, it's the same thing, it's defined. I've clearly drawn a dot in relation to that vapor dome for state 1 and state 2, and then I've clearly drawn the process path between state 1 and state 2. That's what I'm looking for. And I've also got units on there because that's important as well. So complete picture of what's going on. Those little dotted lines that I drew like across for the temperature, and the ones that go vertically from the for the specific volume, you can leave those off. Those are not necessary, but I just put them there for clarity. It's not incorrect if you put them there, but just make sure that it's if you do put a little dotted line, make sure that it's obvious that that's not the process path. The process path is clearly drawn from state 1 to state 2. Okay, so I think I've got everything except that quality, so let's go ahead and get the quality. It's two-phase, and so my specific volume is defined according to that quality. So I'm going to switch that equation around, solve for the quality. I've got the V sub F and V sub G values right there on table A2. I plug it in and I get a quality of 0.0296, which is 2.96%. All right, so now let's go to part B. So it's the temperature is, boy, there would be nice if I had a unit there, but it's okay, pretend there is. My pressure is 30 bar and my temperature is 374.14 degrees Celsius. Okay. All right. So 374.14 degrees Celsius. I go to table A3 just because 30 bar is a nice clean value as opposed to 374.14 degrees Celsius. And I can see in table A3, I'm going to the saturated tables to figure out what phase I'm in. I could see that the saturation temperature at 30 bar is 233.9 degrees Celsius. I'm at 374.14 degrees Celsius, clearly above that saturation temperature, so I know it's superheated. So I need to get out of the saturated tables and go to my superheated tables. All right, so table A4, all of those are your superheated tables. And what I've done here is I've gone to the box that corresponds to 30 bar, and my temperature is 374.14 degrees Celsius, so it's going to be between 360 degrees Celsius and 400 degrees Celsius, and you can see the corresponding specific volumes squared on the right there. So all I need to do is interpolate between those two values, and when I interpolate, I get a value of 0.0948 meters cubed per kilogram. So that's my specific volume. And then you can also see on my TV diagram, I filled in that information. I've got my vapor dome, I've got T1 and T2 clearly labeled. I've got V1 and V2 clearly labeled. I've got the dots drawn in relation to that vapor dome, and I've got the process path drawn between them. So I'm all done. I'd get full credit for that problem. No problem. Okay? All right. Well, thank you for watching, and let me know if you have any questions.